make sure it's recording the right channel too. Yep, it is. Wow, amazing. All right, so I'll just use the my trusty dry board marker here and talk about something that I think will be important. Okay, so the first thing doesn't really need this. Okay, the question is, can I play basketball?
Can you?
Yes.
Oh, yes.
Can I throw? Do you think I'm strong enough to throw a basketball, at least to the level of a hoop?
Yes.
Probably. Okay. Can I land a shot from like half a basketball court away?
You could
Maybe 1 in 200 shots I can.
You could at
lucky
least
shot.
hit it.
I can hit it. Yes, I can hit it. Maybe just for about 15 minutes, then I'll have to sit down and take a break.
Halftime.
Yeah. So the answer is yes, I can shoot a basketball, and occasionally I can even make it through the hoop. Cool. Can I become a professional basketball player?
You could try.
Unlikely, yes. Very unlikely. Okay. Now, how does that have anything to do with programming and math and stuff like that? People can write programs without any math background, just like I can shoot a basketball in the general direction, right? I can throw it. I can just throw it enough, at some point it will land, right? It will land a score. But the question is, can those people who can become a professional software engineer and be hired as one? That really is the differentiation. And I personally think that people with a strong math background are more likely to succeed as a professional software engineer. They can do it for a living, as opposed to doing it as a hobby. Okay, so that's the difference. There are two schools of thought, on this very topic. In other words, what do computer scientists, the big ones, the really famous ones, what do they think about math versus computer science? One guy, his last name is Dijkstra, thinks, well, you have to be you have to be a math major first, and then you can specialize in computer science. That's his way of thinking. Okay. The other guy, his last name is Knuth, K-N-U-T-H. He's still teaching at Stanford University, and his basic feeling is, well, the tools that we are using these days are completely different from the tools that we were using, 15 years ago. 50 years ago, you need to have a lot of mental capacity just to keep track of your program, because the programming languages were very primitive. The tools are also very primitive. So you need a lot of capacity just to keep track of how much code you have written up to this point. But now we have a lot of GUIs, okay, a lot of what we call IDEs, or integrated development environment, where the tool itself is so easy to use, it can help you spot problems a lot of times. So we don't really need to spend a lot of mental juice just to keep track of the program. So his thinking is, with these tools, maybe more people can become programmers or software developers, and they're both right in a way. Okay, you don't need to become a full up 100% mathematician to start programming, but understanding mathematics is going to be helpful. Okay, so having talked about that, we'll kind of move on to talk about what is a precondition as opposed to what is a post-condition. Okay, that really is the whole thing that we want to talk about. Okay, so let's talk about an algorithm. So we'll just use this box here to represent an entire algorithm. Can be something simple, can be something difficult, doesn't matter. The precondition is a condition that has to be true before your algorithm can start execution. Some people can look at this as the constraint of the input. Okay, what do we know about the variables before this algorithm starts? Is that okay so far? Okay, so you can express it as conjunctions, disjunctions, negations, comparisons, and so on and so forth. It's just it has to be true before your algorithm. It's guaranteed before your algorithm starts. The post condition is a condition that is guaranteed when your algorithm finishes its calculation. And once again, it is usually expressed by comparisons and conjunctions, disjunctions, and negations. It's the same kind of stuff that we have been talking about already. Are we still doing okay so far at this point? Okay. I'm going to change the way I present these things a little bit compared to the notes, okay? And I think it makes more sense on the whiteboard. Remember this code here? If x is greater than y, then z gets x, else z gets y, and if. Do you remember this code? What does it do? Or what did I claim that this code would do? Finds the maximum of x and y and use z to store that maximum. That's what I claim. We traced this a few times already using several test cases. Remember that? It worked for all the test cases. No problem. Does that guarantee that it will work all the time? Nope. Does not guarantee that it will work all the time. In other words, a particular algorithm, if you have not found a test case that can break your algorithm, in other words, make it do something incorrectly, does not mean your algorithm is guaranteed to be correct. Because if that was true, it's easy to guarantee an algorithm being correct. Don't test it. Does it make sense? If you don't test something, then you cannot find a flaw of that something. And if that theory is true, if you cannot find a flaw, it is flawless, then you just don't have to test anything. Then it's flawless automatically.
My philosophy.
Well, the fallacy of that theory is it is not flawless. It is simply no discovered flaw. Doesn't mean there's no flaw. It's just not discovered. So the question is, how can I guarantee this algorithm is actually going to find the maximum? Well, the first thing we want to do is to look at this algorithm and say, well, do we have anything that we have to assume about x, y, and z before it starts execution? That really is the first question. What do you think? Other than x has to be a number, y has to be a number, is there anything else that I have to assume in order for this algorithm to start? Nope, nothing, right? Nothing that I really should assume here. So what is a precondition that is true regardless of the condition, regardless of the relationships between x, y, and z? Okay, let me repeat that question because the answer is surprisingly simple. The question is, what is a condition that is guaranteed to be true regardless of the values of all the variables involved in this algorithm?
X and Y are real numbers.
X and real, okay, let's say that that's an assumption already that I do not need to state here.
X and Y are not equal.
Well, they can be equal, and this algorithm should work in that case as well. What about the precondition just being true? The condition of true is guaranteed to be true. Cool. Okay, that's a very strange precondition because what this is saying is I'm not making any assumptions. There are no restrictions to the input of this algorithm. Because true is also true, always true. Okay, it's the simplest way of saying true without saying anything. Okay. What about the post condition in mathematics? How do I say that z is the maximum of x and y? We are kind of familiar with this particular notation, but how do I boil this all the way down to just comparisons and conjunction, disjunction, and negation? Yep.
Z is greater than or equal to x, and z is greater than or equal to y.
Okay. So let's take a look at this one and see if that is truly representing the result of what we want. It's a good starting point, but it's too loose, okay? Because if I want z to be just greater than or equal to x and z is greater than or equal to y, I can just make z a really big number, right? Okay, let's say x starts with a value of 2, y starts with a value of 4. If I make z 2000, that would meet this requirement. But 2000 is not the maximum of 2 and 4. So we need to refine it a little bit.
Z equals X or Z equals Y.
Yep, it has to be the same as one of those two. Okay, so we're just missing this little part here. So we have to say and, but inside this and here we have to say z equals X or z equals y. It has to be the same as one of those two. Z equals x or z equals y. That will do it. Okay. This is what we want as the post condition. Am I making any sense so far? Now, do I know that it has this post condition? Not yet. Okay, we don't really know yet. But this is good. Okay, this really states that z is the maximum of x and y. Are we still doing okay so far with the concept of what is a precondition and what is a post condition? Is that okay? All right. We start with nothing. We want to end up with a conclusion that the algorithm does work the way it's supposed to. So how do we do that? Now, since I don't have a projector, this actually lends itself to making pictures on the fly. So this is a good thing. All right, so we'll draw the picture of a typical conditional statement, because this is a conditional statement. And we'll just go ahead and say this is the condition, x is greater than y. This is the then branch, this is the else branch. And here we have z gets x, here we get z gets y. Are there any questions about the pictorial representation of the algorithm? We have looked at it several times already. Okay. But this time when we look at this, we're going to look at it in a slightly different way. Because what we'll do is we'll say, at this point here, before the branch itself, what is guaranteed?
True.
True. That's it. True is guaranteed to be true. That's all we can say, which is saying almost nothing, right? Okay, well, that's okay. We'll just say pre1 is true. Now, pre1 is saying the precondition of line 1. So the line number is inside the parentheses. And then when we say pre1, it simply means it is the precondition of line 1. Before line 1 executes, what is guaranteed to be true? Are we doing okay so far? Okay. And this simply says, okay, we are not making any assumptions about x, y, or z. We just don't say anything. Are we still doing okay? The next question is over here. This is pre2. In other words, when we are just about to execute line 2, what can be guaranteed?
When x is greater than y.
X is greater than y. Well, technically speaking, it is pre1 and x is greater than y. The reason why that is the case is because whatever the condition is true here still has to be true by the time we get here, because comparisons do not change anything. So whatever in pre1 is true, by the time we get to pre2, still has to be true. In other words, if I want to write it out, pre2 is pre1 and the condition of the conditional statement, which is x is greater than y. Are we doing okay so far with this statement here? Pre1 is a part of pre2 because comparison does not change variables. Whatever was true before the comparison still has to be true after the comparison. Are we doing okay with this statement? Now, what do we know about pre1? Hey, we know that pre1 is true. So now we have true and x is greater than y. I think we can simplify this a little bit. How do we simplify something like this? Well, you kind of have to know, Boolean algebra a little bit to make this happen. Okay, Boolean algebra is just like regular algebra, except it only applies to Boolean values and Boolean operators. Okay, so in arithmetic, we know that x1 times x is just x. Is that established?
Yes.
Okay. Now, is that given to you as an axiom, which means, well, we don't prove this, we just know it is true, or is it proven in your math class?
No, it's true.
It's an axiom, okay? But in Boolean algebra, we can actually prove certain things. So what I'm claiming now is true and whatever. We'll just call it A. Well, we'll call it B for a reason. Okay, we'll just call this B. It's just B. So we have a kind of similar type of identity here, except true is taking the place of 1, and conjunction is taking the place of multiplication. But whatever is on the other side of the conjunction stays the same. In other words, true is the identity of conjunction in Boolean algebra. Is that okay? So I'm just drawing a parallel between algebra that you already know to Boolean algebra, which is something that we're trying to learn here. But how do we know that is true all the time? How do we know this is right? Well, we can actually prove it in Boolean algebra. In Boolean algebra, the nice thing is, if you have A and B as two separate independent Boolean variables, you can only have four possible combinations out of these two. A can be true, A can be false, because it's a Boolean variable. Okay, you can only assume one of two possible values. When A is true, B can be true or false. When A is false, B can be true or false. In other words, you can only end up with four possible combinations between the two independent variables. Is that making sense so far? Okay. So now I can enumerate and say, okay, what is the result of A and B? Well, there are only four possible combinations. There are only four possible results. It's true, false, 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 by the definition of conjunction. How is that helping me to prove this point here? Exactly. If you look at the first two rows, oops.
Give or take.
Okay, if you look at the first two rows like this, you notice the first part is true. Okay, the first part is true here. The second part can be true or false, but you can see the result is really just the second part. Is that making any sense? You can see that when B is true, A and B is true. When B is false, A and B is false as well, as long as A is true all the time. So that proves this is correct. Okay, you can make the simplification. True and B is just B. Am I doing okay so far here? Okay. That can be helpful because now I can take, okay, let me just write this block here. So now that we can see, true and x is greater than y, x is greater than y is really just our b. Okay, I can just now simplify that to x is greater than y. Is that okay? That's the precondition of line 2 in the algorithm. Now, knowing this is the precondition of line 2 of the algorithm, which means every time right before we execute z gets x in the algorithm, we are guaranteed at that point that x is greater than y. Now, don't ask me the exact value of x or the exact value of y, because this doesn't tell me anything about their exact value, but it does tell me that x is greater than y. Is that making any sense? That's the precondition of line 2. Now, if I know this is the precondition of line 2, what do you think is the post-condition of line 2? In other words, after we perform this operation, z gets the value of x, what is now guaranteed?
X is the maximum?
Not quite the maximum, but can we express it just using comparisons and logical operators? Well, first of all, can I keep this? Can I keep x is greater than y being true in the post condition? In other words, does changing z has anything to do with the ordering between x and y?
No.
Nope. So that means it still has to be true. Does it make sense? That x is greater than y still has to be true as the post condition of line 2? Can I say anything else? Because of line 2 itself, can I now claim something that I did not know before?
Z is greater than y.
Z is greater than y, or I can just say that z is x. Okay? The reason why I choose to use z is x instead of x is greater than y is because z equals to x is more specific. So you always want to go for the more specific description so that you retain as much information as possible. Okay? Is that okay with post 2? Now I can now go to line 4 and do about the same thing. So I'm going to use this part of the whiteboard for line 4. What is pre-4? What is the precondition of line 4? What is guaranteed to be true when we get to line 4? We are talking about this part here. What is guaranteed to be true at that point? Okay, we have Well, pre-1 still has to be true because a single comparison cannot change anything, right? But on top of that, we also know the condition has to be false. So the condition of the conditional statement is negated here. Is that okay? As the precondition of line 4. Questions? No questions? Okay. All right. So we can do the same kind of simplification here. Pre-1 is just true, and instead of using a negation in front of a simple comparison, we can just kind of restate it to become x is less than or equal to y. Is that okay? It is not the case that x is greater than y is the same thing as saying x is less than or equal to y. But don't forget the equal part, okay? Because a lot of times people remember the less than part but forgetting the equal part. All right, so using the same technique over there, we can now take true and blah 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 out and just have x is less than or equal to y remaining, and this is the precondition of line 4. In other words, right before line 4 executes, I am guaranteed that x is less than or equal to y. Did I say anything about the exact value of x or the exact value of y? Nope. Doesn't matter. That's not the point of the pre and post condition approach. It's, we just want to know what can be guaranteed. Okay. What about post 4? The post condition of line 4 is going to be, hey, we can borrow this from pre-4 because line 4 does not change x or y. So if x is less than or equal to y before, x is less than or equal to y still has to be true after line 4 executes. Is that okay? But on top of that, we also know one extra thing now because of the assignment statement. What do we know?
Z equals y.
Z equals y. All right, very good. So now we want to focus on post 4 and post 2. Post 4 is stating what do we know when we get out of the else block. Post 2 is stating what do we know after we get out of the then block. Okay? So now we have two ways merging into one. In other words, now I want to make a conclusion of post 5. After the entire conditional statement is done, what can I possibly conclude? Well, somehow we have to look at post 2 and post 4 and combine them into post 5. The question is, what do we do to combine it? In other words, if I'm standing here, drunk, okay, and not remember which way I came from, I just know that I came from one of the two paths, what can I say that has to be true? And here's my bottle. I don't drink actually, but I just thought it'd be funny to use this as an analogy. I woke up here. I know that I came from one of these two paths. I know that if I came from this path, post 2 has to be true. If I came from this path, post 4 has to be true. I'm just standing here right now, dizzy and not know what happened.
Is it x is greater than y or x is less than or equal to y?
Well, I like the or. Post 5 is post 2 or post 4. Just a regular or, not an exclusive or. Okay? An exclusive or means that only one of the two can be true. A simple or means at least one of the two has to be true. Okay? And it is a simple or that we need here. Because I'm just standing here and I say, well, this can be true or that can be true, because they can both be true at the same time, depending on the code that we're dealing with. So that's why we don't want to use an exclusive or and just a regular or. Okay, so let's go ahead and spell out post 5. I know I'm kind of using the whiteboard all over the place. So post 5 is saying something like this. So we are saying, x is greater than y and z equals x, or x is less than or equal to y and z equals y. right? I'm just rewriting, post 2, post 4, and combining both of those into one single kind of messy statement. Are we still doing okay so far? This expression here, this post 5, is derived based on the structure of our pseudocode. This definition here is what we think, hey, that would be a good definition of the maximum of 2 variables. Question is, can I say these 2 are the same? Or if I really want to be lazy, I just want to say, can this imply this? Because to draw a equivalence conclusion is a little bit harder sometimes. If you just want to imply, that will work enough for us. Okay, if the actual derived post condition implies the correct result, it is still correct. It's still good. Okay. The question is, can we make these 2 the same? Can we start with one and turn it into the other one? What do you guys think? So let's, okay, if you're a computer scientist, what would you do? Or what would you want to do? Gonna erase a little bit here so we can actually do the derivation. But I will leave this part up on the board. Okay, so, I'll give you several choices. One, we look at the 2 equations and say, yeah, they both got x, y, and z and a bunch of comparisons. I think they're the same. Or 2, well, I'm going to throw some values here, okay? I'll throw some values to x, y, and z in the first expression. Okay, some of these came out to be, the entire expression sometimes come out to be true, the entire expression sometimes comes out to be false. I throw the same test cases as the second one, and they come out to be exactly the same matching answer as the first one, so I think they're the same. Or third, I'm going to study Boolean algebra and find out how to derive one to the other one.
2.
2. Okay, the problem with 2 is you're reducing everything back to throwing darts. So whatever the flaw of throwing darts is, we end up with the same problems. Okay? So we want to learn enough about the Boolean algebra so that we can actually derive one to the other one. Doesn't matter which way it goes, okay? If you can, because if you have an equivalent relationship here, you can start with either one and end up with the other. Okay. So, but this looks really nasty. I mean, how do we do something like this? Well, fortunately, we have a few tools that can help us. Yep.
Roll sheet.
Roll sheet. It's not going to help here, but it will help something else. Okay. So what we'll do is we'll first take a look at the distributive property of Boolean algebra. How many people still remember what is the distributive property in algebra, regular algebra? Okay. So in regular algebra, you have a plus b, the whole thing in parentheses, times c equal to ac plus bc. Okay. I hope you guys still remember this because that's the entire basis of how we do multiplication, multi-digit multiplication. Okay. Okay, so knowing that, the question now is, do we have something like this in Boolean algebra? Because it would kind of be handy because we have an or here and then a nested and on each side. We have an or here nested inside a conjunction. So it looks like there's something like that may be helpful. Okay, as it turns out, we do have something like this. Okay, so we have A, B, and C as 3 independent variables. So we have true, 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 false, 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 true, true, false, false, true, true, false, false, true, false, true, false, true, false, true, false. Because this time we have 3 independent variables, and as a result there are 2 to the power of 3 possible combinations. Okay, what is the point of this? Well, the point is we want to look at this. Okay, A or B, the whole thing and C as one expression. And on the other side, we want to look at A and B or A and C. And see if they boil down to exactly the same values all the time for all 8 possible cases. Does everybody understand what I'm trying to prove here?
Yeah.
I'm trying to prove the distributive property of in Boolean algebra. Okay, well, this is really just tedium at this point. Because if I know that A is true, B is true, C is true, then this whole thing is going to be true. A and B is true because they're both true. A and C is true because both are true. True or true is true. Okay, let's look at the second row. A and B are both true, so A or B is true, but C is false, so true and false is false. Now we want to look at this one here. Uh-oh. Doesn't work out. A and B is true. A and C is false. So true or false is false. Okay, I messed up somewhere.
Should be A and C and B and C.
A and C. Yep.
Yeah.
Okay. Thank you.
Another one.
I copied it wrong. A and C, B and C. There we go. Thank you.
The one on the left is supposed to represent the one on the bottom, right? So it would be
No, either one. I mean, because you can do it one more time. You can just.
because it says
Right,
A or
yeah.
B
Mhm.
and C, but the
As
way
it
that's-
turns out, the distributive
The other
rule
ones.
also applies in the other direction too, in Boolean algebra. So we'll talk about that next. But we'll go ahead and prove this one first. So A is true, C is false, A and C is false. B is true, C is false, B and C is false. False or false is false. So if you complete this table, you will see that for each row, the answer to this expression matches the answer to that expression, which means these two expressions are equivalent. They are exactly the same thing. Are we still doing okay so far? Okay. So with that information, we can now take this one here and expand it all the way out, because what we can do is to say, hey, you know what? I can look at this part here as one single expression. So now this is my C, and this is my A, and that is my B. Attack, the orders are wrong. Because in that case, we have A and B appearing first, and then C is the last one. So what, if I have to, which property do I have to prove before I can apply that distributive rule to property to here? Commutative, is the one that, let me flip it, and then the one that says, I can do conjunction in any order, but you have a chain of conjunctions, is called associative. So all of those are actually true too. I'm not going to go through the truth table to prove every single one of those, but they are actually true as well. So that means I can now take this thing and apply that technique and have a big, huge, long expression remaining. Okay, and what is that big, huge, long expression? Okay, I'm gonna write here. Z is greater than or equal to x, and Z is greater than or equal to y, and Z equals x is one side of the disjunction. And then the other side of the disjunction is, so we have an or here. The other side is Z is greater than or equal to x, and Z is greater than or equal to y, and Z equals y on the other side. Okay, is that making any sense? Sort of? Okay. We look at this, we look at that, and we ask, okay, can we conclude that these two are exactly the same thing? We're getting closer. There are ways to simplify, okay? Now, if you look at this part here, Z is greater than or equal to x, and Z equals x, they seem related. Do they seem related to you?
Yeah.
So if they're related, is there a way to combine these two into one? Okay. Well, let's just do.
Greater than x.
Hmm?
you no longer need z is greater than x?
That is correct, because you're looking at the intersection, and when one is containing the other one completely, you just look at the one that is being contained and not the containing. So that means this can simplify. This is no longer needed. Okay, that whole thing is not needed. And if you look at this side here, that means y is z is greater than or equal to y is no longer needed. That doesn't look right to me. No, it doesn't look right to me at all. Okay, let me see what am I missing here? Z is greater than or equal to x, z is greater than or equal to y. No, that's okay. That is still okay. Yep. Okay, what is missing is one thing. Okay, I know what we're missing here. Okay, it has to do with the original definition. Okay, z is greater than or equal to x, and z is greater than y. It has to be the same as one of those two. Actually, that is correct. Okay, so now we have to make a match between this and that. Okay, that's a way to do it. That's easy. Okay, if you look at this expression here, x is greater than y and z is equal to x, is there a way to match this sub-expression here to this sub-expression here? It has to do with the transitive property of inequalities.
Since this on the top part, since z is equal to x, on the left hand side you can replace x with z, so it'd be z is greater than y.
But since z is the same as x, and since x is greater than y, doesn't that also mean that z is greater than y?
Yeah.
Now, if we know that z is greater than y, doesn't that also imply that z is greater than or equal to y?
Yes.
Okay, so it goes in one direction, doesn't go back in the other direction. But remember, we just want the implication to go in this direction. That's all that is needed. Is that okay? No? Okay. Well, we'll go over this again on the other day, and then I'll use my notepad to record it. Okay, but I do want to finish this whole thing because we still have about 3 more minutes, and that's more than enough time. If you look at the other one, it says z is the same as y, but we also know that y is greater than or equal to x. Doesn't that also guarantee that z is greater than or equal to x?
Yeah.
Yep. Isn't that what this part is saying? Okay, great. So this is also implying that, at least implying, they're actually equivalent, but I'll just draw implying here. So that means this entire expression implies the actual expression that we have here, which is coming from the definition of the maximum of 2 variables. So what is the conclusion? Okay, if I ignore all the details about how to prove axioms in Boolean algebra and all that stuff, if I ignore all the detail, what have I just done?
Proven it works for all cases.
Values of x and y. Yep. So I no longer need to throw test cases anymore, because I have proven once and for all that for all possible values of x and y, this algorithm will guarantee that z is the maximum of the 2 input variables. Okay. Well, sometimes we get lost in the little details and forgot about what is the whole thing about, right? But that really is what it is about. So is this answering the question that I asked a little bit earlier of what is the place of mathematics in programming? And do you think Microsoft has enough mathematicians? There are not enough mathematicians in the world for any organization, because if this, a 5-line program, requires this much math to prove it, what do you think a program that has millions of lines will require to verify the whole thing from top to bottom?
I knew another program is to prove the program.
Yeah. Well, that's why do you guys remember early on I referred to it as the Holy Grail? That really is the holy grail. Okay, people have been trying to do this for decades. Okay, it's called automated program verification. Okay, that's the official name. And that's also how one branch of artificial intelligence came into existence. It's because they want to prove something like this automatically. You start with the algorithm, you start with the precondition. They want a program that can give us the post condition. So that we don't have to go through all these steps here by hand. Okay? But you can also see why that would be a useful type of program if it can be done. Okay? Unfortunately, it can be done to simple algorithms like this, but it doesn't work for large algorithms. It's just not feasible, just not practical to do it. Okay? So does that mean that topic 3 is now done because it's not practical? Not quite, okay? Not quite. Because the technique and the knowledge that we know that we get practice from by doing this sort of thing is also going to be helpful in one thing that is extremely practical to people who write programs. And I don't even care in this case whether you are a computer scientist or an engineer or a math major who just need to get some program to work for certain things. It has to do with debugging. If your program doesn't do what it's supposed to do, what do you do to fix it? Okay, shaking it, caking it, and knocking it around is not going to help. So we'll talk about what this type of thing has to do with debugging a program on Thursday.